So in the last class, we have seen about number systems. So what are the number systems? So decimal number system, hexadecimal number system, octal, and binary. How to convert these from one system to another system. So today we are going to see the next topic, Boolean algebra. So what is Boolean algebra? So Boolean algebra, put in a larger screen. So Boolean algebra is a mathematical system for manipulation of variables that have only two values. So in Boolean logic, we either say on and off, or 1 and 0, or high or low. So in the formal logic, we say that it is true or false. So in the Boolean logic, you can either say on, off, or 1, 0, or high, low. This is Boolean logic. 1 or 0, high or low, or on and off. So these Boolean expressions are created so on Boolean by using the Boolean variables. So you have to some operations have to be done on the Boolean variables so that we get the Boolean expressions. So the normal common Boolean operators are and or not. So there are some other Boolean operators such as NAND, NOR, XOR and XNOR we see later. So when you ask what is Boolean algebra means, it is a mathematical system for manipulation of variables that have one of two values. So these values will either be on and off, 1 and 0 or high and low. Okay. So normal Boolean operators are and, or, and not. So Boolean operator can be completely described by using a truth table. So what is a truth table? So it can see it is a table. So it has two parts. One it is input, another one is output. So here x and y are inputs. X one input, y another input. Output is only one, x into y. X into y. Okay, so we are calling as xy. So this is the truth table. So x and y have two inputs. So these two inputs have, every input has only two values, either 0 or 1. So 2 inputs, 2 power 2, 4 combinations. You have 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1. So since it is an AND operation, you have to multiply 0 into 0, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, 1. So this is the Boolean AND operation. So there are two inputs, x and y. So Boolean AND operation is x into y. So when you multiply both the inputs, if any one of the input is 0, output is 0. So the Boolean operators for the AND as well as OR are shown in the right hand side. So AND operator is also known as Boolean product. So OR operator is known as Boolean sum. So in the next truth table, you have two inputs x and y. But the output is x plus y. So OR means you have to add these two values. So 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, 1, 1. So the sum is will be going in some other circuit. So we get only the result. Sum and carry. So carry will go to the next circuit. So you take the sum. So 1 plus 1 it is actually 1, 0. But in Boolean OR it is 1 only. Okay. Any one of the input is 1, output is 1. If both the inputs are 1, it is 1 only. It is not normal sum. It is Boolean sum. Boolean sum means 1 plus 1 is 1 only. Next one is NOT operator. So if you give 0, it is output is 1. If you give 1, output is 0. So this NOT operation is represented by in the output you get a x bar, that they are calling as elbow, or sometimes they will give you a complement symbol by using a prime mark like this. For example, if you are writing a Boolean function means it should have a Boolean variable, at least one Boolean variable. It should have at least one Boolean operator. Boolean operator means it may be have a AND operation or OR operation or NOT operation. So it should have a input from the set 0, 1. So it is also a producing a output that is a member of set 0, 1. Here an example is taken, a function x, y, z, three variables f of x, y, z is equal to x z bar plus y. Here, if you look at this equation, you have three Boolean variables x, y and z bar. Actually it is z, it is an operation is done bar, not operation. So x, z bar plus and y. Then you have an AND operation x into z bar. It is a Boolean AND operation. And finally you have a OR operation plus. Okay. So from this expression you have to draw the table. So input x, y, z. So you have to give all the combinations. So 2 power 3, 8 combinations. So you have to write all the 8 combinations. Next one is so we need z bar. So we are taking z bar separately. Then we take a z bar. We have to multiply x into z bar, and finally we have to add with y. So first you take the z bar. It is a complement of z. So whatever z values available, is just complement it. Next one is x z bar. So after complementing it, then you have to multiply with the x. So 1 into 0, 0. 0 into 0, 0. So when it becomes 1 into 1, so then only you get a value of 1. So if you look at this table, here x z bar, x is 1, z bar is 1, so output is 1. Here also x is 1, z bar is 1, output is 1. X, z bar 1, output is 1. So remaining values it becomes 0. So now you have to add this value plus y. So first two inputs 0, here there is 1, so it is 1, 1. Here 1 comes here 0, here also 0. So it becomes 0. Here 1, so automatically 1. So here 0, but here it is 1, so it becomes 1. So likewise you have to do the Boolean operation. So this is normal Boolean operation with Boolean multiplication, Boolean addition and Boolean NOT operation. So digital computers will implement this Boolean function using circuits. So we are implementing in simple Boolean expression means Boolean function means the circuit also simple. So simpler circuits are easier to build, so it consumes less power, consumes run faster when compared to the complex circuits. So we in this mind we have to reduce our Boolean functions to the simplest form. There are a number of Boolean identities too that help us to do this. So most of the Boolean operation you have AND operation, you have OR operation. So how this operation works? So first one, so I am multiplying my 1 into x. So anything multiplied with 1 is x. Next one, when you multiply 0 with x, anything multiplied with 0 is 0. So we are multiplying x into x, output is x only, because x into x is not x squared, so it is once again x only. So this is about the AND form. So similarly you have to give the OR form. So OR form 0 plus x. So whatever value x will be available in the output. For example, I am adding 0 plus 0, output is 0. 0 plus 1, output is 1. So whatever the input in the second input is the output. So 0 plus x is equal to x. So next one is 1 plus x. So 1 plus x is equal to 1. So x if it is 0, 1 plus 0 it is 1 only. 1 plus 1 It is also 1 only. Then x plus x, it is same thing only. So you have to give a single value x. X plus x bar. So whatever present in x will be available, whatever present in not in x will be available in x bar. So W2. So this is about the Boolean and product form and or sum form. So this is another identity, Boolean identity. You should be very familiar when you are studying with algebra. So xy can be written as yx. Xy can be written as yx. X plus y equal to y plus x. X plus y equal to y plus x. Xy into z, you can group anyone. Xy z here first xy is group. The second right hand side it is y z is group. So you can group any variable. Okay. So in R form, this is x plus y plus z equal to so you can interchange the plus value x plus y plus z. Similarly, last law, distributive law, x plus y z can be written as x plus y into x plus z. Similarly, x into y plus z equal to xy plus xz. So another identity, so we have seen, so first identity law, there are several laws in Boolean algebra. First law, so there is in first law itself we have two forms. One is AND form, another one is other OR form. So identity law says that 1 into x is equal to x. So x has either 0 or 1. So 1 into 1 means 1. 1 into 0 means 0. So output is the same value of the x. So 1 into x is equal to x. So in the R form, it is also identity law. 0 plus x equal to x. With 0 plus 1 equal to 1. 0 plus 0 equal to 0. So whatever is the value of x, it will be present there. So this is identity law. Next one is null law. So null law means you have to multiply 0. 0 means it is nothing. 0 into x is 0. Here, in R form, we have to add the full value. So 1 plus x equal to 1. So you have to take the whole value. X is a small value, the whole value. So 1 plus anything is 1 only. Next one is interval law. So same thing you are multiplying. X into x. It is not x squared, it is x only. Okay. So x plus x also, it is not 2x, it is x only. So next one. So inverse law. So x into x bar. So you have to multiply the value with the complement. For example, I am multiplying 0 and 1. So what is the result? 0. So if x equal to 1 means 1 into 0, it is 0. So in the R form, 1 plus 0 is 1 or 0 plus 1 is equal to 1. Okay. These are the first group of laws: identity law, null law, interpolation law, inverse law. So other second group is commutative, associative and distributive. So commutative means you can change the order of the variables. Xy equal to yx, and similarly x plus y equal to y plus x. So associative law is you can group any variables. For example, you have three variables x, y, z. Then you have to multiply yx and x plus y equal to y plus x. This is commutative law. Next one is associative law. So you can group the three variables. You can group any two variables. X, Y, Z means you can group X, Y or Y, Z. That is known as associative law. Similarly, in the R form, X plus Y plus Z, you can either group X plus Y or Y plus Z. So here comes the part distributive law. For example, X plus Y Z can be written as X plus Y into X plus Z. So this is about the second group of Boolean identities. So another group is there that is known as that is very important, absorption law. So X into X plus Y. So it becomes X plus XY, then it becomes X plus 1 plus Y, then finally it becomes X into 1, so it is X only. So De Morgan's law, you know that. So X into Y whole complement equal to X complement plus Y complement. Similarly, there X plus Y whole complement is equal to X complement dot Y complement. This is about the De Morgan's law. So another one is double complement law. So here you have to do the complement two times. X complement is there. You have to do one second complement. It becomes the value of X. Okay. So we have ordered all the laws here. So here there is a equation. We are using the 10 laws we have seen earlier and we are simplifying this. So the equation is very big. X plus Y into X plus Y bar, the X Z bar whole complement. Now we have to first apply the De Morgan's law. X plus Y plus X plus Y bar plus into plus or X plus Y X in plus Z X plus Z Now we have to multiply every component inside. So first two components X into X XS, X into Y bar XY bar, then X into Y XY, Y bar Y into X bar plus Z. So Y bar Y is Y only and X plus then you have to, after multiplication this, you have to group accordingly. So I am grouping X into Y plus Y bar, X bar plus Z into X plus Y bar. So if you look at this, so first what we are doing is we are applying De Morgan's theorem here. So X, this becomes X bar plus Z double complement. So it becomes complement get cancelled. Okay. After this I am multiplying this X into X bar, XX, XY bar, YX, XY and YY bar into X bar plus Z. Now what we are doing is, so X into X is X only. So X plus, so here X is common. So we are taking YY bar here, X plus YY bar. So YY bar is 0. No need to do this. Y into Y bar is 0 only. So you put 0 here. So X plus X is common. So Y plus Y bar. Now X plus 0 plus X into, so this one become Y plus Y bar. So Y plus Y bar. So it is equal to 1. So S plus 0 is 0. X of X bar 1 is what can X of 1 into X bar plus Z. Now what we are doing is we are multiplying this one. So X into X bar plus Z. So now it becomes x into s bar plus z, x bar plus xz, x into z. So it becomes xz. So by using this last, you can simplify any Boolean function. So you have to use the corresponding function. By that you have to simplify the problem. So totally you have 4 laws plus here 3 laws, here 3 more laws. Totally 10 laws are there. So you have to use the corresponding law for the particular step. So normally you should multiply, and if it is x bar means it is 0. For example, it is x into x means it is 1. Okay, it is common for all versions. So remaining things you multiply and you have to use the corresponding formula. You can build a complement, build a circuit in the circuit in the function directly. Okay. So the De Morgan's law provides an easy way of finding the complement of a Boolean function. So De Morgan's law is very useful. For example, xy bar equal to x bar plus y bar. Similarly, x plus y whole bar equal to x bar into y bar. So De Morgan's law can be extended to any number of variables. It is not needed to for it is 2 variables or 3 variables. It can go up to 6 variables. People are putting this at up to 8 variables. So replace each variable by its complement, change all ands to r and r's to and. This is about the De Morgan's law. For example, f of xy is z. It is xy plus x bar z plus y z bar. Then we are putting a complement. So when you put in complement, this plus symbol become and symbol. So xy plus you become and symbol. Similarly 6z plus become and symbol. Next one is common symbol will be above this figure. For example, x means 1 x bar z whole complement, y z bar whole complement, which is equal to. Now we are applying De Morgan's theorem. So x bar plus y bar. Similarly, x bar z whole complement becomes x double bar plus z single bar. So double bar get cancelled, so x plus z double bar. Similarly, yz bar whole equal to y double complement, y single complement plus z double complement, so double complement get cancelled, so y bar z. From this exercise we can, using these laws we can simplify any Boolean expressions. So in order to eliminate the confusion in the course outcomes, so you have to design as will express these Boolean functions in canonical form. So instead of writing in zeros and ones or in variables, they are writing in canonical form. That will be very, very easy. So in the Boolean algebra, we have 2 canonical forms. One it is called sum of products, and another one is called product of sums. So sum of product means there are different products, and finally it is summed up. So product of sum means there are different sums, and finally they are product. Okay. So in the first example, SOP form, sum of products, there are different products like xy, xz, yz. And you have to sum up together to find the original value. Similarly, in the second example, x plus y, y plus z, X plus Z. These are the products available in the second example. So finally you get f of xy equal to x of y plus xz plus yz. It is very easy to calculate the value of the function from the truth table. For example, I have a function f of xy z equal to x z bar means complement, x into z bar plus y. So where we have to take this x, y, z values. So here it is a 3 variable sum. So you have to take all the combinations of the x, y, z. So 2 power 3, 8 combinations. So you have to take all the combinations as input. So output, by using the expression, you have to find out. So it is easy to convert a function to sum of products form using its truth table. So the output should be 1 for SOP form. So using this table, we can list all the values of the variable which is used for the test operation. So the sum of products form for our function is x bar y z. So here the same example is given. So we have looked at Boolean functions in abstract terms. We have seen what is Boolean function in a short way. So we have implement the Boolean functions in digital computer circuits called gates. So what is gate? So gate is an electronic device that produces a result based on two input values. Okay. Gate is an electronic device that produces a result based on 2 or more input values. So in reality, gate consists of 1 to 6 transistors, but digital designer thinks of the as a single unit. So integrated circuits contain collection of gates suited to a particular purpose. So next one is the logic gates. This is very important. So in the last case, they will ask what is Boolean algebra, what are the laws available in Boolean algebra. Otherwise, they will ask the name of the question, state commutative law, state inversion law, De Morgan's theorem. Like this, they will ask independently. Or they will ask as a whole, what are the tools available for this particular course. So here there are 3 simplest gates are used. One is AND, another one is OR, another one is NOT. So in the AND gate, so you have 2 inputs and only 1 output. Next one is OR gate. The symbol is like a curved one. Here also the input is xy, x plus z. So AND gate we have already seen this. If any one of the value is 0, output is 0. In OR gate, all the values will be 2 except then. So finally NOT gate, so it is an inversion. Okay. So another useful gate is XOR gate. The output of the XOR gate is true only when the inputs are different. So XOR gate is if the inputs are the same, the output is high. So there are 2 more gates are there, NAND gate and NOR gate. So NOR gate will produce output only if both the inputs are low. Low means 0. NAND gate, it will produce 1 output. If anyone, both outputs are same, output will be low. If both outputs are different, output will be high. So we are saying NAND gate, NOR gate as universal gate means they are very cheap as well as they are used to make any gate. So any gate can be found from this universal gate. So we are calling this gate as universal gate. So it not only it has 2 inputs, it has multiple inputs, it has 5 inputs, 3 inputs, 4 inputs, 7 inputs, up to any number of inputs it can have. For example, a second output can be produced from the complement of the operation. Here x, y, z, so it will sum up x plus y plus z. For example, if you want y bar, you should give a NOT gate before, then you have to give the y bar here. Then only it will be replicated in the output. So in the output, not only it has Q, it is also have Q bar. If you want the complement, you take the complement of the operation also. That is only they are given. Second output is provided in the logic gate for the complement of the operation. So the combination of gates implement the Boolean function. So for example, you have seen the example earlier. So x plus y bar is z. So y bar is an AND gate, y bar z is an AND gate, and x plus y bar z is an OR gate. So we have designed a circuit that implements the corresponding Boolean function. It is a combinational circuit. So why we are calling it as a combinational circuit means, so combinational circuit will produce the output depending upon the input values applied at that time. So there is one more circuit is called sequential circuit. So sequential circuits produce output not only inputs but also at the previous outputs also. That is one of sequential circuits. So combinational circuits gives us many useful devices such as adder, subtractor and so on. So before going to this, we first see the logic gate. So here, so I will explain one by one. Okay, first logic gates. There are 3 logic gates. So they are called basic gates. So basic gates are AND or NOT. AND or NOT. Okay. So what is a gate? So a gate will transfer the values from the input to the output depending upon the condition. So either it will pass the input or it will produce stop the output, etc. So the basic gate means, so by using this basic gate, you can form any gate. That is known as basic gate. So if you have AND gate, OR gate and NOT gate, but you doesn't have any other gate means, you can form any gate by using this AND or NOT gate. So first AND gate. So while drawing the AND gate, you have to draw a line, straight line. Here also straight line. Here straight line. Then you have to put a curve. There are two inputs for our example. A, B, and Y is the output. Okay. So it has input, it has output. So output is always 1. So in any gate, the output is always a single output. But the output is single line, but the expression may be bigger. Okay. So here the Boolean expression is y equal to A dot B. This is called Boolean product. It is not multiplication. We are calling it product. Boolean product. Y equal to A into B. Y equal to A into B. That is called Boolean expression. These A, B are Boolean variables. These are input, these are output. So whenever you ask any gate, you have to draw the gate, you have to draw the expression, and you have to draw the truth table. So truth table consists of two parts. One it is input. So here input is A and B. Another one is output. Output is Y. So you have two inputs. So we know that in binary it has two values, 0 and 1. So both are 0. A is 0, B is 0. So A is 0, B is 1. Now A becomes 1. So A1, B0, A1, B1. So these are the four combinations you have take from these two inputs. So our expression is A dot B. So A dot B means you have to multiply. 0 into 0, 0. 0 into 1, 0. 1 into 0, 0. 1 into 1, 1. Okay. So when you ask what is truth table means, truth table contains all the combination of inputs, and its corresponding output. Okay. So whenever you ask define AND gate means you have to draw the diagram, you have to write the expression, you have to draw the truth table. So sometimes they will ask what is truth table. So you have to tell truth table contains all the combination of inputs. So it will contain all the combination of the input and its corresponding output. So the AND gate will produce output. So it produces output only when all inputs are high. When all inputs are high. When all inputs are high. So when both the inputs are high, the output is high. So the explanation for AND gate is it will produce output when all the inputs are high. So you have to draw the diagram, Boolean expression, truth table, and finally you have to give the explanation that it will produce output when all inputs are high. Next one is OR gate. So while drawing the OR gate, you have to put a curve like this. Another curve, and you have to draw it. A, B, and 1. Here the expression is y equal to A plus B. Here also it is not a normal addition. It is a Boolean addition. It is a Boolean sum. So what is the difference between normal addition and Boolean addition means? So in normal addition, when you add 1 plus 1, it is 1 0. So in Boolean addition, 1 plus 1 is 1 only. So you have to write the truth table. So A, B, Y. A, B are input, Y is output. So 0, 0, 0, 1, 1, 0, 1, 1. For Boolean addition, 0 plus 0, 0, 0 plus 1, 1, 1. 1 plus 1 is also 1. So now we have to give an explanation that it produces output, it produces high output, so high output, low output, there are two outputs. So it produces high output when any one of the input is high. Both inputs high also high. So at least any one of the inputs should be high. Any one of the input is high. So next one is NOT gate. NOT gate. So here by drawing it is a triangle. So you have to draw this triangle. Then you have to put the inversion. This bubble is called inversion. In digital electronics, bubble means inversion. It is a complement of the output. So it has a input, it has a output. So A is the input, Y is the output. So Y equal to A bar. Y equal to A bar. Okay. This is the Boolean expression. Here there is only one input and only one output. So input is 1, A, output is 1, 0 means 1, 1 means 0. So it produces complement of the output, complement of the input. So it will always produce the complement of the input. Whatever the input, it will produce the complement. So these three gates are called basic gates: AND gate, OR gate and NOT gate. So AND gate means both the inputs are high, output is high. OR gate, if any one of the input is high, not only any one of the input, if both the inputs are high means it will produce the output. So NOT gate, whatever input you give, it will produce the complement of the input. Okay. So these are called basic gate means. So I am giving a expression. So any expression you can form by this AND or NOT gate. So only we are calling as basic gates. So next one is universal gates. Totally there are 7 gates. So we see all the 7 gates, then we see what is universal gate and why we are calling as universal gate. Next gate is NAND gate. So NAND gate is a universal gate and NOR gate is a universal gate. So NAND means inverse NOT and AND gate. So NOT gate and AND gate we are calling as a NAND gate. So the symbol, while drawing the symbol, so you have to draw a line, straight line and a curve and you have to put a inversion. So this is NAND gate, A, B and Y. So expression for this is Y equal to A dot B. First NAND gate expression. So this Y A dot B is the input for the NOT gate. So the output is A dot B whole complement. A dot B whole complement is the Boolean expression for this NAND gate. Now we have to draw the truth table. A, B, Y. You have all combinations 0, 0, 0, 1, 1, 0, 1. Okay. Now, this is a NAND gate. So first you have to multiply A dot B. So A dot B means 0 into 0, 0. There is a complement. So 0 complement is 1. So 0 into 1, 0. 0 complement is 1. 1 into 0, 0. 0 complement is 1. 1 into 1, 1 only. So 1 complement is 0. So while writing the definition for the NAND gate, so you have to write it produces low output. So remaining things we are write high output. So here it produces low output when both inputs are high. Both inputs are high. So high means 1, low means 0. High. So this is the explanation for NAND gate. So next guide is NOR gate. So NOR gate. So it is a combination of OR gate and a NOR gate, similar to NAND gate. So in the NAND gate you have AND and NOT. So here OR and. So while writing the symbol, there is a curve, another curve, and a bubble. So A, B, Y. So Y equal to, first this expression A plus B, then inversion, whole complement. Whole complement. So while writing the truth table, A, B, all possible combinations 0, 1, 1, 0, 1, 1. So Y. So A plus B, first one, A plus B, 0, 0 plus 0, 0, 0 complement 1. So next one, 0 plus 1, 1, 1 complement 0. 1 plus 0, 1, 1 complement 0. 1 plus 1, 1, 1 complement 0. So it will produce a high output. It will produce high output when both inputs are low. When both inputs are low. When both inputs are low. So in this case there is only one mount. So it will produce a high output when both inputs are. There are two more gates, XNOR and XOR. XOR gate. One more gate XNOR is there. So XOR gate, so they have given a symbol like this. You have to draw two curves with parallel, then you have to OR. It is similar to OR gate. This is OR gate. So you have to put a parallel line and you have to take the outputs A, B and 1. Here the expression they have given us Y equal to AB bar plus A bar B. In short form, they have written as A plus what? Otherwise round பண்ணிருக்காங்க. So they have rounded the plus symbol. The actual expression for XOR gate is AB bar plus A bar B. Okay. So in a short form, XNOR gate will be like this. A plus symbol, it is rounded. A, this is called XOR B. Okay. By this symbol we cannot write, so you have to write the truth table according to this form. So while writing this truth table, you have to write this combination also, then only you can easily understand. So it is a big table. So you have to draw A, B bar, A bar B. So I am drawing A bar, B bar. Okay. Then only it will be easy. Okay. So this is AB. I have also written A bar, B bar. Okay. Now A, B bar. So next A bar, B. Finally A, B bar plus A bar. Okay. So you have to write all the combinations 0, 0, 0, 1, 1, 0, 1. So first write the complement of all the combinations. So you first write the A, 0 means 1, 0 means 1, 0, 0. So here 0 means 1, 1 means 0, 0 means 1, 1 means 0. Now you find the product, this product, first next product next. So this product is A, B bar. So A into B bar is A into B bar, 0 into 1, 0. Next one, 0 into 0, 0. 1 into 1, 1. 1 into 0, 0. Similarly, A bar B. A bar B. 1 into 0, 0. 1 into 1, 1. 0 into 0, 0. 0 into 1, 0. Next, finally, you have to add this. So 0 plus 0, 0. 0 plus 1, 1. 1 plus 0, 1. 0 plus 0, 0. For XOR gate, you have to take the expression, these are inputs. Okay? This is output, final output. So remaining time for understanding, I am writing this. So what is A bar, what is B bar? Then while multiplying A into B bar, you get an output. So while multiplying A bar B, you get another output. Then finally, you have to Boolean sum this output, you get the output. So here, if you look at this, both inputs are 0 means. Both inputs are 0 means output is 0. Both inputs are high means output is 0. If the inputs are different, 0 and 1 and 1 and 0, the output is high. So while writing the explanation, so it produces output, high output. It produces high output when both inputs are different. Both the inputs are different. Both inputs are different. When the inputs are different, output is high. When the inputs are same, output is low. So the next one is XNOR gate. Totally there are 7 gates only. So XNOR gate is an inversion of XOR gate. So XNOR gate is inversion of XOR gate. So after the XOR gate, you put an inversion. Then it becomes the XOR gate. So here, the equation is A, B plus A bar, B bar. A, B plus A bar, B bar. So in short form, they have written like this. They are using a minus symbol with a circle for XNOR gate. So the actual expression is AB plus A bar, B bar. Okay. So here also you have to draw a big table, then only you can understand. A, B, A bar, B bar, AB, A bar, B bar, AB plus A bar, B bar. That is output Y. Okay. So you have to write all the combinations 0, 0, 0, 1, 1, 0, 1, 0, 1, 1. So 0, 0 means 1, 1, 0, 0. So 0 means 1, 0, 1, 0. Now AB. So you have to multiply these two. 0, 0, 0, 1. So here A bar, B bar. 1, 0, 0, 0. So you have to add these two. 1, 0, 0, 1. So in this gate, when the inputs are same, the output is high. When the inputs are same, output is high. When the inputs are different, output is low. So it produces high output when both the inputs are same. Then when both inputs are different, you get a high output in XOR gate. Here when both inputs are same, you get a output of. Hello? Hello?
Sir, voice is breaking.
Voice breaking, yeah. Hello? It produces high output when both inputs are same. Now?
Now it is okay, sir.
Okay. So this is about XNOR gate. So you have seen totally 7 gates. AND gate, OR gate, NOT gate, NAND and OR, XOR and XNOR. So NAND gate will produce high output when both the inputs are high. OR gate will produce any one of the input is high. NOT gate will always produce a complement of the input. NAND gate will produce low output when both inputs are high. NOR gate will produce high output when both inputs are low. XOR gate will produce high output when both inputs are different. XNOR gate will produce high output when both inputs are same. Okay. So after seeing this, all these gates, we see why we are calling as universal gate, NAND gate as well as NOR gate. So universal gate means any gate can be formed by using this universal gate. So if I have doesn't have OR gate, if I have NAND gates alone, I can form a OR gate using NAND gate. So I will draw this how we can define a OR gate. So any form gate, that is what we are calling as universal gate. So I am taking NAND gate as an example. So NAND gate. So I want to form a NOT gate by using NAND gate. So what I do is, this is NAND gate. So I want to form a NOT gate by using the NAND gate. So I have to connect these two inputs together. And I put a single input A. This is Y. Okay. Actual expression is A dot B whole complement. Okay. So I am making both the inputs same. So it becomes A dot A complement. So A dot A complement. So A into A is A only. So it becomes A bar. So it becomes a NOT gate. So we can form any gate by using this universal gate. So this is NOT gate. So now I am drawing about AND gate. So this is NOT gate. So I want to have a AND gate. So I want to form a AND gate. So first have a NAND gate. Now the expression is A dot B complement. Then you have to put a NOT gate. So NOT gate we have already seen this. Okay. So when it comes here, so it becomes A dot B double complement. Because it is a NOT gate. So double complement get cancelled, you get a value of A dot B. This is a expression for AND gate. Okay. So by using NOT gate, what I'm doing is, I'm connecting the two inputs together. The expression becomes A dot B becomes A dot A. A into A is A only, so it becomes the expression for the NOT gate. For forming the AND gate, I'm using first an AND gate, so it is A dot B complement. Then I'm using an AND gate that's a NOT gate. So the output becomes another complement. So double complement get cancelled, so you get the expression for the AND gate. So next one is OR gate. For forming the OR gate, so you require more gates. So this is one AND gate, this is another AND gate. So one input you have to give A bar here, another A, and here it is B. You get A bar and B bar here. Okay, you get A bar and B bar here. Next you have to connect another NAND gate. So here the actual expression is A bar dot B bar whole complement. So because A bar is one input, B bar is another input, expression for NAND gate is A bar dot B bar whole complement. By using De Morgan's theorem, we can return as A double bar plus B double bar. So double bar get cancelled, so it is A plus B. So which is the expression for OR gate. So if I want NOR gate, I have to connect here another NAND gate as NOT gate. So this expression becomes NOR gate. So any gate can be found by this universal gate. So we are calling as universal gates. You can form a NOT gate, you can form a AND gate, you can form a OR gate or NOR gate, XOR gate also you can form. So it is somewhat bigger, XOR and XNOR. Okay. So this is about NAND gate as a universal gate. So I will draw about the NOR gate as a universal gate. So NOR gate has similar thing, expression is different. So here also you have to connect these two inputs together for NOT gate, A and Y. So NOT gate, so I want to form a NOT gate using NOR gate. So actual expression is A Y equal to A plus B complement. So here B is also A, so A plus A complement. So A plus A is A bar. So A plus A is A bar. Next one is you can form a OR gate. So actual initially it is an OR gate. Then you have to connect a NOT gate. So you have to use the NOR gate as a NOT gate. So A B, here Y. So here the expression is A plus B complement. Here it is A plus B double complement. So it becomes A plus B. Okay. So which is a expression for OR gate. So I want to form a AND gate using NOR gate. Then you have to use three NOR gates, 1, 2 and 3. So if I want to form NAND gate means you have to use 4 NAND gates, 1, 2, 3, 4. So you have to connect inputs together, then you have to connect here. Similarly here also. Okay. This is AND, this is NAND. What I am doing is, so here I am giving A, so it becomes A bar. Here B, so it becomes B bar. So here when it comes A bar plus B bar, whole bar. Okay. So it becomes A double bar plus B dot B double bar, which is equal to A dot B. Okay. So it is an AND gate expression. Here also A, B, A bar, B bar. So this expression is A dot B here. So here when it comes, it becomes A dot B complement. So by using an AND gate, NOR gate as a NOT gate, it becomes A bar, here B bar. So when it arrives here, so actual expression is A plus B complement. So here A is A bar, B is B bar and complement here. By using De Morgan's theorem, so this plus becomes dot, this complement will go here and the complement will be arrived here. So A double complement, product B double complement. So it becomes A dot B. Okay. So here it is A dot B. So when I am using another NOR gate as NOT gate, it becomes A dot B bar. So this is the expression for AND gate. This is the expression for NAND gate. So you can also form XOR gate and XNOR gate. That is your homework. So you do it on Friday and come. So this is all about logic gates. Next we see how to move from truth table to circuit diagram and circuit diagram to truth table, etc. So I have given an expression like this, y equal to ABC plus AC bar. So I am asked to find the truth table. So it is a somewhat big expression. So I have to simplify the expression. Then I am going to the truth table. So here, while simplification, normal simplification, so A is common in both. So you can take A outside, BC plus C bar. Okay. Is there any simplification? No. So you go to the truth table. So in the truth table, you have three variables A, B, C. There is C bar also. You have to find the C bar from C. And finally, you have to do the operation. Okay. So while writing the truth table, you have to give all the inputs. So you have A, B and C. You have C bar also, you have to find. Then C bar you have find. There is another product called BC. So you have to find the BC. Then you have to sum up this BC plus C bar. You have a column called BC plus C bar. Finally, you have to multiply with the A dot BC plus C bar. For this expression, you have to write the truth table like this. Okay. So ABC, I doesn't know any value, so I have to take all the combination. Okay. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. 1 0 0 1 0 1 1 1 0 1 1 1. Okay. I am taking all the combinations. Next, I have to find the C bar from C. 1 0 1 0 1 0 1 0. Next, I have to multiply B and C. 0 and 0 0 0 1 0 1 0 0 1. Now I have to sum up these two values 1 0 1 1 1 0 1 1. Now I have to multiply with A. 4 values 0. Whatever value here, it is 0 only. Then here all 1, so it will be replicated here 1 0 1 1. Okay. So this is the truth table for this particular expression. So whenever an expression is given, you have to, if possible, you simplify the expression. So after simplification, you have to take all the inputs here and you have to find every variable. This is an operation. C bar is an operation. So I have put a column here. So plus is operation. BC is an operation. Product. So I am putting a column there. Plus is an operation. So I am putting a column here. So finally you have a product A into this value. So I am putting another expression. So this is the final output. Remaining are intermediate output. So you can do it manually, but if you write everything, the answer will be very perfect. There will not be any error. Okay. So you should know how to write a truth table from the expression. How to write a truth table from the expression. Next one. So I will give a diagram. So from the diagram I have to find the expression. From the diagram I have to extract the expression. So this is the diagram that is given to me. So I have to find the output Y. So while finding the output, what I have to do means I have to come from left side to right side. I have to start from the left side. I have to finish with the right side. So this is stage 1. So these two operations will done parallelly. This is stage 2. There is only one element. Here it is stage 3. Okay. So in the stage 1, so here what is the output? You have to write this. It is an AND operation, so it is A dot B. So it is an AND operation. The inputs are A and B. The output is A dot B. So next one is here it is an OR operation. The inputs are A bar and C. So it is A bar plus E. Okay. Now this is first stage is over. Next I am going to the second stage. Here there is a OR gate. This is one input. This is another input. So A dot B is one input plus here A bar plus C. This is another input. So these two inputs are added together. So this is stage 2. When it reaches stage 3, you have to take whole complement. So A dot B plus A bar plus C whole complement. Hello? So A dot B plus A bar plus C whole complement.
Yes, sir.
Hello? Okay.
Nothing, sir, nothing.
Okay. So we get the final expression. So there is a whole complement. Now you can simplify the expression. So I have taken the final expression. If possible, I can simplify. Okay. So there are 4 inputs. So I have to move stage by stage. So first stage I have an AND gate and a OR gate. Second stage there is only one OR gate. Third stage there is only one NOT gate. So you have to, this is AND gate, the expression is A dot B because the input is A and B. This is OR gate, so the input is A bar and C, so A bar plus C. This is another OR gate, this is one input, this is another input. So A dot B is one input, A bar plus C is another input, you have to put A plus here. This is a NOT gate, so you have to take the whole complement. Now we have to simplify this because there is a De Morgan's theorem. So Y equal to A dot B plus A bar plus C whole complement. So now I am applying the De Morgan's theorem. This plus becomes dot. So A dot B whole complement. Here A bar plus C whole complement. Now also you can simplify. So this becomes A bar plus B bar dot. This is A double complement dot C single complement. So it becomes A bar plus B bar. So A complement is A only, double complement get cancelled. Here it is C bar. Okay. Now there are two expressions. One it is A bar plus B bar, another one is AC. It is by product. Now you can multiply everything. So you can A bar, A, C, one product. So I am multiplying this one with this. Then I am multiplying this one with this. B bar, A, C. Okay. C bar, B bar, A, C bar. You know that A bar and A. So A0 means A bar 1. A1 means A bar 0. So 0 and 1 will get cancelled. So this term becomes 0. So remaining term only available B bar, AC bar, which is equal to A into B bar, C bar. This is the final expression. So I have a diagram. I am splitting the diagram into different stages. I am moving from one stage to another stage. Finally, I get a expression. So after getting the expression, so I am applying the Boolean laws. So some terms get cancelled. So after the terms get cancelled, I get the final expression, which is A, B bar, C bar. So this whole circuit can be replaced by a single circuit, 3 input AND gate. So for example, I am drawing the circuit. I can use a 3 input AND gate and 2 NOT gates. So A, B, C. So this is the final expression. So the same operation can be done by these 3 gates. Here 1, 2, 3, 4 gates. So same operation can be done by 3 gates. So simplification is very important in digital electronics. So wherever you get an expression, if possible, you try to simplify it by using the Boolean laws. Okay. So you have to study the Boolean laws. So we see in the afternoon what is Boolean laws. We go very depth and how we can use the Boolean laws to simplify the equation. Here I am using, first I am using De Morgan's theorem. I am using the De Morgan's theorem. Here also I am using De Morgan's theorem. Then this is the double inversion formula. So double complement becomes same only. So after this it is normal multiplication. So here it is also a formula. A bar into A is 0. So this is remaining term only present in the final output. So we have to very strong in the Boolean algebra, Boolean laws, then only you can simplify the equation. Okay. So this is about how to derive a Boolean expression from the diagram and simplification. Here how to draw a truth table from the expression. How to draw a truth table from the expression. So next I will give one expression. Then you have to draw the diagram. From the expression how to draw the diagram. So I am giving a big expression. You have to draw the diagram. So y equal to AB C bar plus AB bar plus A bar B plus C bar D. Okay. So this is an expression given. You have to draw the symbols, draw the logic gate. You have to draw the circuit connection. They will ask draw the circuit connection. So first we have to, before simplification, so I can see this A by B bar plus A bar B, it is a XOR gate. Okay. So I can return as A B C bar plus A XOR B plus C bar B. From the expression A B bar plus A bar B, I can understand that it is XOR gate. So I replace this with an XOR gate, A XOR B. Now it is no more simplification is possible. So So you can simplify C bar. C bar is common here and there. So C bar AB plus D plus AX or B. AX or B. That's all. So now we have to draw the diagram. So what is the first stage? So this plus is the final stage. Okay, this plus is the final stage. So first stage is AB. AB is the first stage. So AB is the first stage. A and B. So this A and B is added with D. So you have to give a XOR gate. This is second stage. Okay. This is second stage. Then in this output is inversion. So here AB plus D is done. At the same time you have to do the inversion. You have to do the inversion C. Here it is C. Then only you can multiply with the C bar. Then you have to give a AND gate. AND gate and AND gate. Okay. So after doing this operation, you have to do XOR gate. So you have to add this. For this, you require a XOR gate here. Then only you can add. This is Y. So this is A and B. Okay. So first stage is this one. Second stage, this one. Third stage, this one. Fourth stage, this one. So first I have to multiply A and B. Then only I can add with D. So while adding D, you have to do the C complement also. So then only you can add these two products in the next stage. So while adding D, I have to take the C complement in the same time. Okay. Then I am multiplying this. So after doing multiplication, you have to add this value. So before adding this value, you have to process this value. So I am using a XNOR gate, the third stage itself, and I am finding A and B. So I get the A XOR B here, and similarly I get this product here. So then I am finally adding, and I am doing this operation. So this is the circuit diagram for this particular expression. From the expression, you have to think of how we can simplify the expression. So after simplification, you have to draw the diagram. So you have to keep the logic circuit properly. So this inversion gate will come in the which stage? You should know it is a second stage. Similarly, this XNOR gate should come in the third stage. You should not put in the first stage because it will create a long delay. Okay? So it should come in the third stage. And you finally get the. So in the afternoon class, we see in detail about the Boolean theorem and how to simplify the equations. This is an introduction class only. We see later in depth about Boolean theorems. Mohammad Ijaz. Mohammad Ijaz. Naveen.
He's not replying, sir.
Yes, sir. Naveen.
Sir.
What are the logic gates you have seen so far? How many logic gates and what are the logic gates?